Hey everyone, Miss Butler here. So cohort B, you're watching this in class. Cohort A, you're watching this at home because of Labor Day. But I got a nice video for you to introduce Beer's Law, which is going to be the topic for the week, and we're going to do some labs. Before we get into Beer's Law, I did grade your very first lab, so I have a couple things to share that maybe will help you with the labs that we're going to do this week. If you are in class, you can get your lab notebook and kind of look through it. If you are not in class, you can get your lab notebook when you're back in school. And any pre-lab type stuff that we're doing for future labs, if you don't have your lab notebook, just do it on loose leaf paper and we'll staple it in. All right, a couple of analysis questions from that very first lab. Number 4, does the mass of the salt have to be exactly 2.000 grams? Why or why not? It does not need to be exactly 2 grams, but we want to get as close as possible, right? Any more, it might not dissolve. Any less, we might not have a strong enough concentration. But the important part of this is that you need to record the exact amount you get. So if you got 2.010 grams, you need to record that in your data table because we will use those numbers in calculations. I actually think, especially with our really good balances, it's a little shady when kids get right on the money because very rarely are those even staying at a single number for a long amount of time because of that estimated digit and it's the sensitivity of the balance. Number 5, does the initial volume of deionized water actually matter? And then which graduated cylinder did you use? So the amount did not really matter. I did have you record as close to your 5 milliliters as you could get, but you ended up adding more anyways. So you needed enough to dissolve the salt, but not too much to overflow your volumetric flask. And then one thing, the graduated cylinders we had out actually were 10 milliliters, but the markings were every 0.16 milliliters, which is kind of bizarre. So I did accept in your data table if you rounded to the 10th place, one spot past the decimal, or the 100th place when you recorded, just because markings every 0.16 is a little strange. And then why was the silver nitrate added? So just to be clear, it was not added to see if the beaker was clean. You clean the beaker at the beginning and then you dissolve salt water. Technically it is not clean at that point in time, even though you transferred it out. The point was to see if there was a precipitate. The question though is, what was that precipitate? Well, if there was any salt left in your beaker, I added aqueous, AgNO3. It's a double replacement reaction, so we are going to create NaNO3, which is aqueous, and AgCl, which is one of the exceptions for chlorine, is with silver, so that would be a solid. I can break this into the net ionic equation, Na plus aqueous plus Cl minus aqueous, Ag plus NO3 minus makes Na plus. And so what was really going on, if I cross off all my spectator ions, is that Cl minus and Ag plus, both aqueous, made AgCl solid. So this was the precipitate, the cloudiness we saw. It was the chlorine of the salt reacting with the Ag, the silver of the silver nitrate. Okay, so 11, draw what happens to the chloride ion through the course of the quantitative transfer. So first, we should be drawing particle pictures. So that means we are zoomed all the way in. Oops, sorry guys. We are zoomed all the way in to see the particles. This is not just pictures of you stirring and salt water and things like that. We're zooming in. And so we started with salt. Na and Cl bonded together. And notice that when they are bonded together, it's neutral. Overall, we are neutral in charge because for every one Na plus atom or ion, there is one Cl minus ion. But when we put it in the water, we are going to break apart into the ions. And some of you did a really good job of even drawing the water and how it surrounds, the way it lines up to surround the plus and how it lines up to surround the minus. That's fine. You did not have to do that, but I was looking for you to show me that it broke apart. Then we did a transfer. So we tried to get rid of all the Na plus and all the Cl minus, but maybe there was a little bit left over. And so what we added then was AgNO3. So we added Ag and NO3 to that, and what should have happened is we should have formed then a precipitate if you had stuff left over. So this is your precipitate, and that leaves the Na plus and the NO3 minus just floating as spectators. Okay, so I need you guys to be accurate and precise about the way you use those words. A lot of you use the wrong word, which changes your entire statement. I'm thinking more, I think it was question 6. So for example, the graduated cylinder is not more or less accurate than the volumetric. If you read it correctly, then it is accurate. So it doesn't, when you're comparing a graduated cylinder, the markings don't make it more or less accurate. Accuracy is that you drop down, you squat, you read from the meniscus at eye level. But the volumetric flask, on the other hand, is precise to one value because it's calibrated to that value. So again, it's not that we're talking about accuracy here, we're talking about precision. It's precise, very precise to one number. For volumetric flask, the uncertainty is printed on the side of it. So you should have in your data table had 2 places past the decimal, but as long as you got the meniscus just touching the line, it should have been both zeros. So no matter what volumetric flask you had, you should have in your data table had 0.00 for your decimal places. And that only is good for that specific number, whether you had a 100 milliliter flask, a 250, 1,000. And then one other thing, if you even glance at a calculator when solving a problem, you need to show that work, and measured values need to have units. All right, so over the weekend, you should have looked at molarity, moles per liter, and then dilutions, M1 times V1 equals M2 times V2. So I'd like you to pause the video and try this dilution problem. You are solving for M2. All right, here's my answer. You can check your work. It is okay, even though molarity is technically moles per liter. For M1, V1, if both volumes are milliliters, you can leave them. Or if it makes you more comfortable, change them both to liters. That's fine. It won't make a difference with your answer. But as long as both volumes match, it's okay that they are in milliliters. All right, on the agenda for today is an active link to this simulation. Here's what I would like you to do. In the drop-down, open up the simulation. So you'll pause this video once I'm done with the directions. Open up the simulation in a different tab, and you'll change the solute to potassium permanganate, which was the last problem. Add a shake of that to this solution, and then you can drag this piece right here so it hovers and it'll tell you the concentration. I want you to get the concentration and jot it down, and then I would like you to add some water to it and see what it does to the concentration. And then I would also like you to remove some water and see what that does to the concentration. So please pause this video, go and do those 3 things. Add the KMNO4, write down the concentration, add some water, get the new concentration, and then remove water and get the final concentration. All right, so hopefully you saw that by adding 1 shake, you could get a certain concentration depending on how much of the solid you added, depends what your concentration is. When you added water, that diluted the sample, and so you have a lower concentration, a new concentration. Mine was 0.102. And then finally, I asked you to remove some water, and I hope you notice that the concentration stayed the same. The reason that is because when we remove the liquid, we are also removing some of the dissolved KMNO4, right? So the ratio of the amount of liquid removed and the amount of KMNO4 should have stayed the same. So really the only way to change the concentration once we've added the solid is either to add more liquid, which will dilute it, or add more of the solid. By just taking away some of it and draining it, that did not change the concentration. All right, so we practiced molarity. Now let's apply it to this new concept called Beers-Lambert law, or I call it Beer's law. All right, so kinetics is the study of reaction rates, which is what our next unit's going to be all about. But in general, chemists need a way to monitor, when they're studying kinetics, the concentration, the molarity of reactants and products over time. That's how we study the rate of reactions or how fast they're going. But we can't see molecules, right? They're way too small, so we can't tell and count them if they're being used up or if they're forming. But there's other ways we get around this. We might measure if a precipitate is forming. We might measure the mass over time as it's starting to form, or maybe the pressure of a gas over time. If it's getting used up, the pressure goes down. If we're making it, the pressure goes up. The volume of a gas, if I'm making it, it's going to be an increase in volume. But what if there isn't a phase change? What if we're not making a precipitate? What if we're not changing a gas and using it up and making something else, right? We need another way to study concentrations of reactants and products. In order to do this, we can use something called spectroscopy, which is how light interacts with matter. So molecules will absorb light and emit light depending on the types of bonds. And when they absorb that light and then emit it, we might see different colors, and that's all based off the types of bonds in the molecules. So with spectroscopy, what we can do is we can utilize a color change to look at the progress of a reaction. So this picture is actually a reaction we'll see later this year. It's crystal violet with sodium hydroxide, and over time that reaction becomes lighter and lighter and lighter. And so what we can do is we can monitor the rate or the progress of the reaction based off how the different shades of purple interact with the light. It also works if there's a reaction with a big color change between reactants and products. Maybe my reactants are a light yellow shade and then they turn bright pink. Any differences we can also use spectroscopy for to measure the change in concentrations. So to do that in our class, we can use either a spectrophotometer or a colorimeter. In our class, we are going to use a colorimeter, but I want you to pause this video and watch this 58-second video. The link is on the agenda, and it tells you how a spectrophotometer works. I'm sorry it's not very exciting, but it gets the job done and it's less than a minute. So pause this video and watch the short video clip on how a spectrophotometer works. The link is in the agenda. All right, so in our class, we're going to use these colorimeters, but before we start, you always have to set it to the optimal wavelength. So what I see on here is we have options for 430 nanometers, 470, 565 nanometers, and 635 nanometers. So what you do is you're going to use this color wheel, and let's pretend I'm testing a red solution. It is red in color. Well, I want the wavelength of light that's going through this guy to be opposite or complementary the color of the solution. So I'm going to choose to set the wavelength to the green, which is anything between 450 and 560. So I would probably set this one to 470. So I'm going to have this guy set. You just move the arrows until it's lit up, until it's 470. So we'll use this color wheel to help us based off the color of our solution. Before you actually test anything, you'll set it to the proper wavelength and open it up. And inside you'll see a little arrow. That's the way that the light is traveling. So we need to calibrate this, and we're going to calibrate it with a cuvette. This is a cuvette filled with deionized water. Couple of things. The cuvettes have, I don't know if you can tell, but two of the sides are clear, and two of the sides have these kind of ribs or markings on them. When you carry a cuvette, you should touch the sides that have the markings because we don't want to get our fingerprints on the clear side because that could absorb some light. The way we put our DI water in here, we squirt a little in there. You'll take a Kleenex, rub off the clear sides, and then remember we're carrying it touching the rib sides. And we're gonna put it in so that the clear sides face the arrow. So this is a clear side right here. This is a clear side down here because the light is gonna travel through in this direction, up and down. Okay, I'll close it. We'll hit calibrate. I'm trying to keep it flat because you should always keep it flat. We'll hit calibrate, and then when it's plugged in to the LabQuest, it should read an absorbance of 0 because water will not absorb any light. Then we can actually take our sample and put it in. Remember, we wipe it off. I did that ahead of time. Clear sides facing that arrow, and then we can get the reading of the absorbance once this guy is plugged in to our LabQuest. So I get these absorbances. What do they actually mean, and how are they helpful? Well, we can monitor the absorbance of a reaction over time, which is kinetics. So if we were doing that purple crystal violet lab, we know it's going from dark purple to light purple. We should see less absorbance because less light will be absorbed as it gets lighter and lighter and lighter. Or what we're going to do this week is we are going to use it to determine the concentration of an unknown solution. So we'll go into detail about how to do that, but using absorbances of known solutions, I can then take that information and try to figure out the concentration of an unknown solution once I know its absorbance. So before we get into how we will actually figure out the concentration of an unknown substance, let me go into Beer's law, or Beer-Lambert law. So the equation for Beer's law is A equals ABC. Capital A equals lowercase a, b, c. This is on your equation sheet for AP Chem, but here's how it works. What's happening when we put the cuvette in the colorimeter is we have an original intensity of light going through the solution. Well, the solution is going to absorb some of that light, and we can measure how long the light travels through that solution. And on the other side, there's going to be a new intensity of light, because we would assume that if some of the light is absorbed in this area, we would have less light coming out on the other side. So capital A is our absorption, how much light is actually getting absorbed. Little a is a constant. It is the measure of how well a compound absorbs a given wavelength of light. It's called molar absorptivity. And so this is going to be a constant for every substance. So any substance will have its own little a value. B is the path length. So that's how far the light travels through the colored solution. All of our cuvettes that we are going to use in our class are 1 centimeter long. So we will use that. And then concentration is in molarity. Sometimes our molarities are very, very small, so it's useful to, instead of using molarity, it's useful to use micrometers, like this. And to go from a small molarity to micromolar, you will multiply your regular molarity by 10 to the 6, and now it'll be in micromolars. So for us, if I'm using the same solution, little a is going to be constant. And since all of my cuvettes are 1 centimeter, little b is going to be constant. So what we can see here is that as long as we're using the same chemical, A and B are constant, absorbance is going to be directly related to concentration. So if my concentration goes up, so does my absorbance. Right? If I dilute my sample, I will decrease my absorbance. So how can I use this direct relationship between absorbance and concentration to figure out an unknown? Well, here's how we're going to do it. If I give you a stock solution, and a stock solution implies we know the concentration, I can take that sample and I can put it in the colorimeter and record the absorbance and get a point. So I have 1 point right now. And then what if I dilute that sample in half? So I do an M1V1, I figure out a new concentration, and then I measure that absorbance. And then what if I dilute it again to even less? And I measure that absorbance, right? So we know the concentration each time because we can do M1V1. I measure the absorbances, and what we can get is a straight line. And in that straight line, we can get an equation, y equals mx plus b. Well, in this case, y is my absorbance equals the slope of the line times the concentration, right? X-axis is concentration, plus b, which is our y-intercept, like always. So I have this graph, I have this equation, and now let's say I have some unknown sample. And the unknown sample has to contain some level of the same stuff, right? But I don't know the molarity of it. Like the stock concentration, I knew the molarity of it. I knew this guy because of M1V1. I knew this guy because of M1V1. I have an unknown molarity. Well, what if I measure the absorbance and it falls right here? Well, I can go over to that line, and the absorbance is here, so I can find the concentration if I have the graph. A better way to do that, because this is AP Chem, is I can plug the absorbance in here. I know the slope of the line, I know the y-intercept, and we can solve for the missing piece here. So that is how we will use Beer's law, the relationship between absorbance and concentration, and the unknown molarity to find, or the unknown solution's absorbance to find its concentration. Notice I didn't actually use A equals ABC in this process, right? I use the idea of Beer's law is that absorbance is directly related to concentration. That is what allowed me to make the equation or the line of best fit y equals mx plus b. So we're not actually plugging in to A equals ABC. We are just using the concept to solve for the missing concentration. So how could we do M1V1? Well, let's use an example. Let's say I have 0.4 molar of CuSO4. If I take 10 milliliters of that and 0 mils of water, I would have 0.4 molar. What if I take 8 milliliters of the CuSO4? So I take 0.4 molar times 8 mils equals M2, and I add 2 mils of water, so my new total volume is 10. I can solve for M2, which is the new molarity. Same thing now if I take 6 mils. That's my new volume. The total is still 10, right? 6 mils and 4 of water. And so I'm just constantly doing M1V1 equals M2V2 to solve for these new molarities. And each time we're using less of the CuSO4 and more water. Notice the total is always adding up to 10. So these would be, this would be 1, 2, 3, 4, 5 points that we could use on our calibration graph to get a line of best fit, and then we would be able to test an unknown. All right, you should have a handout for the analysis of food dyes and beverage lab where you're gonna do this idea, make a calibration graph and test an unknown. I am gonna have you work in groups of 3 because we don't have block days, so we have to be a little creative, and we're gonna try to be as prepared as possible in this video so that you can come in, grab goggles, and start working. So cohort B, you're here in school today, you're gonna make your groups of 3. Cohort A, you are gonna choose your groups as you walk in tomorrow, making groups of 3. Okay, so partner 1 will be in charge of red, partner 2 is blue, and partner 3 is yellow. I'm working right now, it's Labor Day today, on the stock solutions. So I have the stock solutions behind me. I am working on calculating and measuring the stock solution molarity. So we'll have that on the agenda. It'll say stock solution molarity. You should go to that. Or if you're in class, I can tell you those. But unfortunately, our lab quests are still charging, so I can't actually get my measurements that I need. So I will have that for you for the lab. But here's what you're gonna do. You're gonna read the handout. It gives you some good background. You are gonna draw the procedure. So it is up to you to write your own detailed procedure today of how to do this. Use the information in the video and any hints I've given in order to write the proper procedure. You will complete the dilution calculations, which is calculation number 1 if you look at the calculation section. I need you to do it for all 3 colors. So that's a lot of M1V1, lots of practice, show all of your work with units. So really you're doing the purpose, drawing your procedure, right? So we'll draw out all the steps, set up your data tables and your calculations. So again, one more time for those of you who are snoozing, you need to do the purpose in your lab notebook, or if you don't have it, on a separate sheet of paper in pen, please. You need to draw your procedure, which you are coming up with based off what you learned in this video. You need to set up your data tables. There are data tables given to you. I need you to copy those in your lab notebook so it's ready to go. And then you need to do calculation number 1 for all 3 samples. And you can find the stock molarity in the agenda because I'm going to do it right as soon as I'm done with this video. So again, in your lab notebook, the purpose, you are just reading the background information. Procedure, which is up to you to draw. You will copy these data tables into your lab notebook. You can get this stock solution concentration, stock solution concentration, stock solution concentration. You can get that from the agenda on Canvas. And then prior to coming to class, you are doing calculation number 1 for all 3 colors. Right here it says at least 1. I have edited that on your page. It should say all 3. You are doing all 3 M1V1, or all 3 colors with multiple M1V1s. If I were you, I would use this as a guide. So obviously we're not using CuSO4, we're using red dye, blue dye, and yellow dye, but you will be given the known concentration here. We don't really need to do totals of 10 because the cuvette is very small, right? We're already gonna be wasting. So here's a suggestion for you. And again, ignore these numbers, but once we have the known concentration, we can do one where we have 5 mils of the stock, 0 mils of water, 4 of the stock, 1 of the water, 3, 2, 2, 3, 1, 4. And you can use M1V1 then to calculate the new molarities once I give you the stock solution, which should be on the agenda for Canvas. Some tips for you. Let me see if I can, probably not. All right, I'm gonna go to another slide and I'm gonna show you. So this should be a tip to help you with your procedure for drawings, but let me show you the equipment available on another slide. All right, so when you get to class, you will have a station ready to go like this. It'll have deionized water, test tube rack, graduated cylinder, and a small beaker. I suggest you work maybe like it with your partners nearby. They're kind of sectioned in 3s. Some partners do have the good distilled water, so you can share those if you need a more precise or, I don't know, concentrated spray. Over here are the stock solutions. Again, I will get you the known molarities for these. I'm still crunching those numbers. But what you can do is you can take your small little beaker and you can pour what you, fill it up with whatever your color is. You'll need to grab a colorimeter. They're in these boxes. And you will need to grab a lab quest. I'm working on getting some more, but we might have to be creative and share. Other things that are available to you: test tubes. I find that it's best to mix in a test tube and then transfer to the cuvette. So here's those cuvettes. I will also have boxes of Kleenex to wipe off the clear sides. These guys are great for just transferring small amounts from the test tube to the cuvette. And then we have a few of the volumetric pipettes. So it looks like I got 8 here, so we'll have to either share or using those graduated cylinders will be fine. Maybe we'll use these for the solutions, like the stock solutions, and then the graduated cylinders for the water. I don't know, we'll have to be creative with how many kids are here. So that's all of your supplies. That should help you. Again, I would mix your dilutions in the test tubes and then transfer to the cuvettes, and then you should be able to efficiently do your measurements. So the colorimeter will plug straight in to the channel on the lab quest, and then it should register and give you the absorbance. So it should be a quick thing. Once your dilutions are done, we should be able to efficiently test all of those, and you can create your graphs on your own time using either Excel or your graphing calculator or your or Google Sheets, but you will need to be able to print out your graphs and share them with your group. So find a way that works for everyone. So what are your actual unknowns, right? We're using the stock solution to make that nice graph with the straight line. Gatorade is going to be what we are testing. So I will have purchased a blue, a red, and a yellow Gatorade, and whatever color you have, that will be your unknown. So before the end of class, you will be responsible. I'll have them up front with the stock solutions. You will be responsible for taking one of those disposable pipettes, getting a little bit of your Gatorade, putting it straight into the cuvette, and then testing it. So you can get your unknown absorbance, and once you have your graph produced, you'll be able to determine what the concentration of blue dye, of red dye, and of yellow dye is in your Gatorade. All right, so we need to be really efficient when we come in. You'll find your group and find a spot to work and start collecting your data. So you'll do your dilutions, get your absorbances. You can create your graphs. That can be done on your own time, but you need a way to share with everyone. So you need to be able, you need it so that your whole group can print them out. Everyone can get the equations of the lines. We're just dividing and conquering who's doing all the dilutions. You need to test your unknown. So you don't need to test all of them. Just if you are red dye, you'll test red dye. And then you'll need to finish up the lab when you are at home. This is a formative grade, but we are doing a similar lab next Monday and Tuesday that will be an interim grade. So let's work out all the kinks, learn what we need to learn so we can all do well on the interim grade.